Hello and welcome to our next installment of Learning Trigonometry, where we take a look at the graphs of inverse trig functions. So we're going to graph these functions, inverse cosine, inverse sine, and inverse tangent. And then we're also going to look at a couple of important identities revolving the inverse functions. Identities are equations that are always true. And solve some problems using these identities, okay? So the graphs we'll start off with, I just want to show you these graphs, and hopefully it will kind of reinforce again how you get the graph of a inverse by reflecting across the line y equals x, and the domain and ranges of these functions. I'm not going to ask you to solve many problems around the graphs. I just want you to know how to sketch them and say what their domain and range are. The identities I'm actually going to have you solve problems using. So there's going to be two parts to this video. The first part about graphs, the second part about identities. So let's dive into the graphs of these inverse functions. So here are some learning objectives in this video. We're going to draw the graphs of the three inverse trig functions: inverse cosine, inverse sine, inverse tangent. We're going to use inverse trig functions to solve problems like we did in the last lesson, and then we're going to compose inverse trig functions together. So, you know, what does it mean to do cos inverse of sine, or to do sine inverse of cosine, and stuff like that. So that's a composition. It really reinforces these definitions very well. Okay, so we're going to look at the graph of inverse cosine first. So I have a little Desmos app to look at. There we go. Whoops. Okay, so here's the graph of cosine restricted to be 1 to 1. Remember, cosine's graph goes from negative infinity to positive infinity, and it repeats a bunch of times, so it's very much not 1 to 1. If we want to make it 1 to 1, we just take a snapshot close to 0, where it passes the horizontal line test. So starting at x equals 0, we can go all the way to pi before we fail the horizontal line test. So that's what the graph of cosine looks like. And this is called the principal branch of cosine. It's the part of cosine close to 0 that's 1 to 1. So this chunk is all we get. Now, to get the graph of inverse cosine, remember, our handy-dandy way to find the graph of an inverse function is to draw the line y equals x and then reflect the graph across this line, which means pick a point and swap its x and y coordinates, and that will be on the inverse function's graph. So let's go ahead and do that for this point right here. So 0, 1, which is on the graph of cosine, is going to end up being 1, 0 on the graph of the inverse function. Okay, let's just start adding in some points. This point over here, that's pi over 2, 0, becomes 0 pi over 2. 0 pi over 2. We're already starting to see some shape to the inverse function. Whoops. There we go. So we have these 2 points. And then if we zoom out a little bit, pi negative 1, this point down here, pi negative 1 becomes negative 1 pi. So we'll swap those x and y values, negative 1 pi. That's over there. So we can start to see some shape to this graph. This point comes down here, this point comes up here, and this point goes up to there, to negative 1 pi. Let's go ahead and put cos inverse in, and voila, there we go. That's the graph of the inverse cosine function. So inverse cosine goes from negative 1 to 1. That's its domain. The inverse cosine domain is from negative 1 to 1, and its range is from 0 to pi. The range of values is from 0, we're looking at the y values this time, 0 all the way up to pi. Okay, so that is the graph of inverse cosine. We took cosine's graph, restricted it down to the principal branch from 0 to pi, and then we reflected it across the line y equals x. So again, our order to get the graph of inverse cosine was we started with cosine, we shrunk it so that it had a domain that was 1 to 1, close to 0, and then we reflected that graph across the line y equals x. That gives us the graph of cosine inverse. This is a weird function. It should look a little odd to you. Cosine inverse has a really small domain. It only goes from -1 to 1. It also has a really small range. It only goes from 0 to pi. So it's a really kind of tight function that only is defined for a couple of values of x and only gives you a couple of values of angles out, right? So, but that's cosine inverse, okay? Sine inverse is going to be similar looking to this one. So let's move on to sine inverse. All right, again, we start with the principal branch of sine. This chunk of sine's graph is called the principal branch, and that's the amount of sine, the graph of sine that's 1 to 1, close to 0. So the biggest domain close to x equals 0, where sine is 1 to 1. We start at -pi/2 and we go all the way to pi/2. That's our domain. Our range is -1 to 1. We get all the y values out we can from sine. Again, like we did for cosine inverse or for any inverse function, we graph the line y equals x, and then we reflect each point across this line. And reflecting across this line just means swapping x and y values. So let's take a point and do that. 0, 0, that's an easy one. 0, 0, and 0, 0. That stays where it is. Let's do another point over here. Pi/2, 1. So if we plug pi/2 into sine, we get 1 out. So if we swap those numbers, we get put 1 in and get pi/2 out instead. 1 pi/2. And let's see, where did that go? That's, oops, it's gone because I put a comma. So it's right there. And then this point down here that's at -pi/2, -1, when we swap those around, we get -1, -pi/2. So -1, -pi/2. So, oops, another point. Okay, so we can start to see the graph of sine inverse begin to take shape. It's going to look a lot like the graph of sine, but it's going to curve kind of in the opposite way. It's going to bend the opposite way. So let's go ahead and graph inverse sine in there. There it is. It's symmetric across that line, y equals x. It's like a mirror. It's been flipped across that line. So again, kind of a weird graph. Sine inverse is only defined between -1. This is an x coordinate of -1. This is a x coordinate of 1. So its domain is only from -1 to 1. The range goes from -pi/2 to pi/2. So -pi/2 is the smallest y, and pi/2 is the biggest y you can get out from inverse sine. Okay, so there's inverse sine's graph. Note that it has the same domain as inverse cosine, but it has a different range. Okay. All right, let's do one more. Last but not least, the graph of inverse tangent. This is the principal branch of inverse tangent. Note that our x's go from -pi/2, not including, can't plug -pi/2 in, to pi/2, not including, can't plug pi/2 in. But everything in between those numbers, between -pi/2 and pi/2, and our y's, our range, is all real numbers. Our answers are all real numbers. We can get any slope out. Okay? So again, our procedure for getting the graph of the inverse function is to graph y equals x. That's the line y equals x. And then reflect the graph of tangent, or the graph of our function, across this line. Again, this is the principal branch of tangent. It's the 1-to-1 part of tangent that is close to 0. Tangent repeats itself many, many times, just like sine and cosine, and we can't use those repeated parts in the inverse function because then it's no longer 1-to-1. It's no longer one answer. So there's our line y equals x, and then we're going to take some points and flip it across this line. We know 0, 0. That's a great one. That's an easy one to flip. 0, 0 is still 0, 0. We have this point here, which is pi/4, 1. So if we flip pi/4, 1, that becomes 1 pi/4. And then we have the negative 1 over here, negative pi over 4, negative 1. That's another nice value. So negative 1, negative pi over 4. Oops, that should be negative. These are all points on the inverse function. And then there's other ones down here. We can swap them if we want to, but we'll go ahead and just graph the inverse of tangent in there. So note that the tangents graph had this vertical asymptote at x equals pi over 2. We're going to put these vertical asymptotes in, x equals pi over 2 and x equals negative pi over 2. These vertical asymptotes, I'm going to go ahead and style them a particular way. So there's our vertical asymptotes for the graph of tangent. The inverse tangent is going to have two horizontal asymptotes, meaning that those vertical asymptotes, when they got reflected across the line y equals x, became horizontal asymptotes. So you can see that this line is going to keep getting closer and closer to the value of pi over 2, but never actually reach the value of pi over 2. So this is going to have this horizontal asymptote. This is a weird function. It's got two different horizontal asymptotes. We have a horizontal asymptote at pi over 2, and we have another horizontal asymptote at negative pi over 2. This is probably the first time we've seen a function with two different horizontal asymptotes. But it's possible, and inverse tangent is just such a function. If we zoom way out, we can see that this red line, which is the graph of inverse tangent, approaches that y equals pi over 2 line, and as we move to the left, the graph of inverse tangent approaches that y value negative pi over 2. And so that's what's going to happen for the end behavior, for the extremes of this inverse tangent. Okay? But again, to graph it, all we needed to do was take our tangent function, just a snapshot close to 0, from negative pi over 2 to pi over 2, and then reflect each of those points across the line y equals x. So this point right here, say negative 1.3 something 4, ends up becoming 4 1.3 something. So that comes over here. Okay, so this point gets reflected. All right, those are the graphs of the inverse functions. You want to be able to know the domains and ranges for each of these and their graphs. How do you get the graph from the original? What does it mean to be the principal branch? Okay, those are the key things, key takeaways from this. Just to remind you on what these domains and ranges are, I'm going to go ahead and just put this slide back in here. I already have this slide from the last video. Cosine, sine, and tangents domains that are 1 to 1 are 0 to pi, negative pi over 2 to pi over 2 for sine, inclusive, negative pi over 2 to pi over 2, exclusive for tangent. The ranges of those functions are negative 1 to 1, negative 1 to 1, and all real numbers. Okay, cosine and sine have the same range, but different domains for what's 1 to 1. Inverse functions are the flips of these, right? So inverse cosine, you put in a number from negative 1 to 1, it gives you an angle from 0 to pi. Inverse sine, you put in a number from negative 1 to 1, it gives you an angle from negative pi over 2 to pi over 2. Inverse tangent, you put in any number, which is a slope, and it gives you an angle from negative pi over 2 to pi over 2. Okay, so those are those three functions. Again, this is where that weird asymptote behavior is, that horizontal asymptote. It gets really close to pi over 2 but never hits it. And in the other direction, it gets really close to negative pi over 2 but never hits it. That's our end behavior for the inverse tangent. Okay, so that's about the graphs. Now we're moving on into the section of this video that's about some useful identities. Okay, so we're going to kind of reason out these identities in this next part and then use them to solve a couple of problems. So here's one super useful identity that relates inverse cosine and inverse sine together. So this t stands for any number. So t, whoops, get the color going. T can be any number that's in the domain for these functions. So it can be any number from -1 to 1. It doesn't make sense to take the inverse cosine of numbers less than -1 or greater than 1. So this is only value if this is only valid as an equation if you can actually take the inverse cosine and inverse tangent or inverse sine of this number t, whatever it is. But if you take the inverse cosine of it and you take the inverse sine of it, whatever t is, and you add those together, you always get pi over 2. Why? Good question. Let's go ahead and diagram this out and understand what is this talking about. Well, let's look at this first statement, cos inverse of t. What does that mean? Cos inverse of t, cos inverse of t is equal to theta. It's equal to an angle. Remember, the answer to cosine inverse is an angle. The answer to cosine inverse is an angle. So it's, what angle is it? Well, it's the angle where we take the cosine such that cosine of theta equals t. Okay? So it is the angle you take the cosine of and get t. How useful is that? Well, it gives us a picture. Let's draw a picture. Okay? So we're saying that cos inverse of t is an angle where the cosine is t. Remember, cosine being t means their x-coordinate is t. So let's just pick a random t. Let's pick anything. So we'll say t is here, for example. So that's a random positive t, okay? And so cosine of theta is t, means the x-coordinate is t. That's why I chose t on my x-axis, because it's the x-coordinate. So we're going to go ahead and graph the angle. We're going to draw the angle in for theta. This angle is theta, okay? So here's our triangle. This angle right here is the cosine inverse of t. So again, this is t comma whatever. The x-coordinate is t for this point. This is the cosine. This angle theta here is cosine inverse of t. Okay? So now we're going to diagram sine inverse of t. What is sine inverse of t? Sine inverse of t is another theta angle, whatever. Put those two together. Another angle, so maybe we can't use theta, so we'll use a different letter. And a common second letter is this one, which is phi, P-I. So this one is theta. So we'll call this one phi. Sine inverse of t equals the angle phi such that sine of phi equals t. So now we have a slightly different picture to draw, okay? Here's our other picture. I'm going to need another color to keep these. So now, same t as before. So whatever our t was we picked for cos inverse, it's the same t now we're picking for sine inverse. So this segment here is congruent to this segment here. Okay? Same kind of picture. Now we're going to sketch this is our point on the go. Draw that. All we know is the y-coordinate is, okay? Never mind about the x-coordinate, that's unimportant in this case. So I want you to notice that these two triangles are in fact the same triangle. The red triangle, I'm going to blow them up a little bit bigger so it's easier. This red triangle, whose side lengths are t1 and theta, is the same triangle as the green triangle. They're just kind of tilted around, okay? So let's look at the green triangle over here. Here's the green triangle. Again, side lengths are 1, t. And where is theta? This is phi right here. This is phi. So let's go ahead and just try to kind of copy these angles around. Where should they go? So t and this t, these are the same t's, okay? Hypotenuses are 1. In this picture over here for the green triangle, my angle phi is opposite t. Well, that's going to be this angle in the red triangle. That's got to be phi, okay? And my angle theta is adjacent to t. That's adjacent to t. So this has to be the angle theta right here. And so what we've shown now is that theta plus phi add up to pi over 2. So it says that theta plus phi equals pi over 2. These angles are complementary to each other. They add up to 90 degrees. They add up to pi over 2. And if we go back to what we said cosine inverse was t, or cosine inverse of t was theta. So this is theta. This is cosine inverse of t. This is cosine inverse of t. And phi was sine inverse of t. Okay, so this is sine inverse of t. So this is sine inverse of t. So these angles are complementary to each other. Okay, so what that says is no matter what t is, cosine inverse of that plus sine inverse of that equals pi over 2. They're complementary angles. I would encourage you to take this a step further and justify for yourself that this identity holds for negative values of t. That you still get the same answer if t is negative. Because in our picture, we picked a random positive t. We were in quadrant 1, but it's actually still true in quadrant if t is a negative value. Okay, they'll still add up to pi over 2. Okay, next, cosine inverse of t plus cosine inverse of negative t equals pi. Okay, so here's our next identity that we're going to look at. So we're going to go ahead and sketch the unit circle. We're going to pick a random value of t. Okay, random value for t. Here we go. Boom. My random value of t. The cosine, again, cos inverse of t equals the angle where cosine of that angle equals t. Again, this is my x-coordinate on the unit circle, and theta is the angle. So cosine inverse is the angle. So here's my x-coordinate on the unit circle. My x-coordinate is t. I'm going to draw the radius, drawing the angle. So this is theta. Okay, boom. So here's my random x-coordinate. I just picked a random positive value. Now, let's look at what's cosine inverse of negative t. So cosine inverse of negative t is another angle. So we got to use a different name, okay? So we've already used theta. Let's use phi. So cosine inverse negative t equals the angle, another angle, where cosine of phi equals negative t. So now I'm taking t and flipping it across to the negative side. So what does that look like? If this is where t is for being positive, then this is where t is as negative. So this is negative t over here. Okay? So this would be a positive x. This is its negative. So this is phi. This angle is going to be what phi is. So that's phi. Okay? Hopefully from this diagram we can see then these two angles, theta and phi, are supplementary. Theta, whoops, let's use because we got them. Theta plus phi add up to pi. Okay? So they are supplementary angles to one another. If it's not super clear why that's the case, I'm going to just show you that this these angles these are the same triangles, so these angles are congruent here. So if I took green, which is phi, I take green and I add on to it this bit here, which is theta, I get to 180 or pi. Okay, so theta, or excuse me, phi plus this bit adds up to pi, and that bit right there is theta. And so these angles are supplementary. Cosine inverse of t plus cosine inverse of negative t to pi. Okay, we'll do one more. Sine inverse of t plus sine inverse of negative t equals 0. Again, let's draw the diagram. Again, these are only true. This only makes sense if t is a value from -1 to 1. It's true for any t in that set of numbers, though. Okay, so the first thing is saying sine inverse of t equals the angle where sine of the angle equals t. Okay? The second part is saying sine inverse of negative t is another angle where sine of that is negative t. Okay? So now we've got some pictures to draw. We'll do the red triangle first. So the red triangle, we pick any random y coordinate, any random value for t. So let's go ahead and make t be up here, for example. So there's t. So that's the point on the unit circle. This is my angle. And again, all we know is the sine is t. The sine of theta is t. So here's theta. Okay. And now we're going to sketch in the green triangle. So we know the sine of phi is negative t. So here would be negative t. It's the same amount but as t but negative. So this point on the unit circle has that, sine. And this would be phi. And hopefully we can see from this picture, these are congruent triangles. They're copies of one another. And so then these angles have to be the same absolute value. They're congruent to each other, but they're negatives of each other. So if we were to add them together, you would cancel out and get 0. Theta is a positive amount, and phi is a negative amount, and they're the same absolute value, the same total amount. And so that tells us that theta plus phi equals 0 because they're going to cancel each other out. They have the same amount, absolute value, but one's counting counterclockwise as positive, the other's counting clockwise, and that's negative, and so they will cancel each other out and add to 0. So that's our third identity that will be useful. Okay, now we're going to do a couple of examples. You could pause the video here if you want and take a break and come back, but we're going to do a couple of examples using these identities. Yeah, so I'm going to re-diagram each of these out so that hopefully it reinforces what we just looked at when we were drawing, rather than just blindly using those identities that we just taught. So take a break, come back, bring some tea, and then restart the video and we'll do some examples together. Okay, so suppose t is a number where the cosine inverse of t equals 1. So this is possible because 1 is between 0 and pi. So it's in that set of possible answers to cosine inverse. We want to compute cosine inverse of negative t, we're going to compute sine inverse of t, and we're going to compute sine inverse of negative t. These are 3 things to compute. And we're going to draw the picture, and then we're also going to just apply these, apply those identities that we just learned. Okay. So first up, cosine inverse of t equals 1. Well, that says, okay, cosine inverse of t equals 1. I don't know why I wrote 0. Let's erase that. Well, what that says is that cosine inverse of t, cosine of 1 equals t. Now we could actually compute this, find out what t is, but it's totally unnecessary to solve this problem. Okay? All I want is to sketch this angle. So an angle of 1 radians we learned was around, was somewhere in quadrant 1. So that means that my t is a positive amount. somewhere in quadrant 1. So we'll just go ahead and sketch this in, maybe something like this. So this would be t. Okay? So what we're going to do for cosine inverse of negative t is sketch in this equals theta, where cosine of theta equals negative t. So we need to take our x that was positive and now flip it across so that it's negative. So I'll use a green color for this. So here's negative t over here. And from this picture we can see that this angle and the angle inside the red triangle are supplementary. And so that means that this one has to add with the other one to get to pi. So that tells us that, well, you're going to use green, we'll say cosine inverse of negative t plus 1 equals, okay, the 1 being cosine inverse of t. So that tells us then that cosine inverse of negative t equals pi minus 1. So there's our first computation done. Cosine inverse of negative t is pi minus 1. To compute sine inverse of t, we remember these guys are complementary angles. So this is complementary to sine inverse of t. Again, that is, if we were to draw this, oops, oh no, go back. Let's draw in this as a yellow triangle. So that means now my y-coordinate is t. So I sketch this triangle in, and so this is t, the y-coordinate being t. And so we've taken that red triangle and tilted it on its side. That angle, therefore, then is the complement to the cosine inverse of t, the angle 1. So this one has to be pi over 2 minus 1. Okay? And here, let's just use that formula that we spent all that time working on. So the cosine inverse of t plus the sine inverse of t equals pi over 2. And this guy here is 1. So sine inverse of t equals pi over 2 minus 1. So we've computed sine inverse of t. And then lastly, we'll use that to find sine inverse of negative t. So negative t would be down here for sine. So that would be this triangle down here. Oh, I should use a different color. Rats. Different color. Oops. Problem. Different color. Here's negative t. Boom. Boom. Right triangle. And so clearly we can see that the sine inverse of negative t is the same but negative of sine inverse of t. So remembering this formula, sine inverse of t plus sine inverse of negative t equals 0. And this guy here is pi over 2 minus 1. Sine inverse 0. So we're going to go ahead and solve for sine inverse of negative t. We can add 1 and subtract pi over 2. So that tells us that sine inverse of negative t equals 1 minus pi over 2. So it's simply the negative of sine inverse of t. Okay. All right. Those are 3 computations based off of the original cosine inverse of t equals 1. We computed cosine inverse of negative t. It's the supplement to cosine inverse of t. We computed sine inverse of t. It was the complement to cosine inverse of t. And we computed sine inverse of negative t. It was the negative of sine inverse of t. Okay? All right, so those are 3. Let's move on to the next example. Let's evaluate cosine of sine inverse of 4 over 5. So sine inverse of 45 is the angle between negative pi over 2 and pi over 2, where sine is 4/5. So we're going to draw a diagram to model this and then figure out what cosine of that angle is, okay? So it's the angle from negative pi over 2 to pi over 2 where the sine is 4 over 5. So our angle, somewhere, we know sine is positive, so that means we're in quadrant 1, and so it's something like this. That would be our angle. Oops. So this is 4/5, and this is 1. So I'm going to take the triangle over here and make it a little bigger. 1 and 4/5. I'm going to scale it up a bit so that it's easier to work with. Or we can just go forth finding out what the x is and find cosine. Here's theta, right? So again, if I were to kind of think of this as cosine of theta, this is my theta right here. This is equal to x over 1, right? X over 1 from that diagram. And so to find x, we just use the Pythagorean theorem. So we can do that. We can go forth and find x. We could also scale the triangle up. This is a simple triangle we've seen. You've probably seen in the past, the 3, 4, 5 right triangle. But I'll just use it as the triangle we see here with 1 and 4/5 as their sides. So we have x squared plus 4 over 5 squared equals 1. And so this is x squared plus 16 over 25 equals 1. And so x squared equals 25 minus 16 over 25, which is 9 over 25. And so then x equals 3/5 plus or minus. And we know that it's positive 3/5. Here's, oops, 3 over, we know it's positive 3 over 5 because theta is in quadrant 1. Okay? So therefore the cosine of sine inverse of 4/5 is 3/5. Fantastic. Okay, last example and slightly trickier. I'm going to evaluate the sine of cosine inverse of negative 0.3. Remember, cosine inverse of negative 0.3, I could kind of just get rid of this and put an angle in here. Okay, so it's sine of an angle where that angle is between 0 and pi, and the cosine is negative 0.3. Again, let's draw a diagram. Here's our diagram. We need the cosine of theta to be negative 0.3. So here's negative 0.3 abouts, and the angle for theta. It's theta, and this is negative 0.3. The cosine is negative 0.3. We're interested in the sine, which is the y-coordinate. So this is negative 0.3 something, okay? And that's the 1. So let's go ahead and blow this triangle up a bit. We know this is negative 0.3, this is 1, this is y, the thing we're interested in. And since it's in quadrant 2, we know it's in quadrant 2 because theta is between 0 and pi, so that's quadrants 1 and 2. We know it's in quadrant 2 because it's where cosine's negative. Now we just have to, so that means the sine is positive, so this is going to be positive. It's going to be something greater than 0. So we just need to use the Pythagorean theorem to find it. So we know y squared plus, I'm going to write this using a fraction, negative 3/10 squared equals 1. Negative 0.3 is negative 3/10. So this is 9 over 100 equals 100 over 100 plus squared. So this ends up being 91 over 100 equals y squared. So y equals plus or minus square root 91 over 10. But in this case, we know it's positive root 91 over 10 because it's in quadrant 2. So that's what the result is. A bit trickier because we have to keep track of the quadrant we're working in, and it's not quite as nice of a value as that previous one. Okay, so hopefully this gave you some additional understanding about these inverse functions, how you can compose them together and so forth, and how you can compute how can you use some of those identities to find results of inverse sine or inverse cosine or so forth based off of what you already know. Okay, so with that, I will leave you to it, and I'll see you in class next time.